Okay, let's get started. Hello, everyone. Thanks for coming to today's discussion session. Today we will work on some problems related to graph theory and go over two problems from quiz 4. Let's start it with the first one. Please use 2 minutes to think about it, and then we will work on it together. And please feel free to unmute yourself or type the main idea or theorem you'd like to use for this question in the chat window. Let's recall what is a simple graph. A simple graph is a graph with no loops and no parallel edges. Also, then what is the degree of a node? So a degree of a node is the number of times the node appear as the endpoint of an edge. So let's get started. We can use the theorem 3 on page 513 of the textbook to prove this problem. Page 413. Okay, as given, all the nodes, we have all the nodes, all the n nodes have a degree of at least 2. Which means then the sum of the degree, the sum of the degrees of all nodes are at least 2n. Any question about this statement? Okay, then by the theorem 3, in any graph, the sum, in any graph, the sum of degree if the toy is twice the number, or is equal to twice the number of ages. This is what theorem 3 said. So the ages, the number of ages is at least 2n divided by 2, which means n. So we are done with this proof. Any questions so far? Okay, the main idea of this question is to use the theorem 3 on page 513. Then let's go to the next problem. This problem is an easier one. Please use 1 minute to think about it, and then we will work on it together. Let's draw the graph first. So we have 4 nodes, 1, 2, 3, 4. And according to the relationship, we have an age from 1 to 1. Then we have an age from 2 to 3, age from 3 to 2, age from 4 to 1. And I will move 4 here. Then we have 4 to 1 and 4 to 4. And then we needed to create the adjacency matrix. And because we have 4 nodes, so the matrix should be 4 by 4. So we have 1 on 1, 1, 1 on 2, 3, 1 on 3, 2, 1 on 4, 1, and 1 on 4, 4. And we should write zeros to other positions. So we are done with this question. If we don't have any questions, then we go to the next one. Okay, this is a harder one. Please use 3 minutes to think about it, and then we will work on it together. Okay, I will show my main idea to solve this problem first. So according to the problem, it says there exists a work from U to V in G. So suppose there is a work from U to V, and if I remove the cycles in the work, then this work, which has no repeated vertices, is a path. So I will claim this path exists on G. So we can start it with started with a G, started with a work on G. So that W is a work on G with the shortest possible length. And we can denote W as U to U is the node vertices. Then next is the edge. H0, H1. V1, E2, V2 to En, Vn. Okay, I can use to the last vertices is V from U to V. We can denote, we can write down the work as this way, and we know the W is the length of W is N because we have N edges in this work. Then we claim because it is the shortest possible length, because this is the work with the shortest possible length, then we can, I claim this work is the path on G. Then we needed to prove this claim is true. Then we needed to prove this statement is true. We can prove it by contradiction. So what is a path? A path is a work with no repeated vertices. So if we want to prove this we want to prove W is the path, we need to prove W does not contain any repeated vertices. If we want to prove it by contradiction, then we assume that there are repeated vertices in W. We assume Vi is equal to Vj and I is smaller than j. Then, so in this one, in this assumption, W has repeated vertices. Then we can write down it at this way from U, E1, V1, E2, V2 to Vi, EI, plus 1, Vi plus 1 to Vj, Ej plus 1, Vj plus 1 to En V. Then we can, so if we have Vi equal to Vj, then we can remove this part. We can remove the work from Vi to Vj. Then V prime is equal to Vi Ej plus 1, Vj plus 1 to. So if we remove Ei plus 1 to Vj, V prime is still a work from U to V. So this is contradiction because we claim W is the shortest work on from U to V on G. Therefore, we can claim G. Therefore, we claim G has no repeat. W has no repeated vertices. Which means W is a path. Okay, we are done with this question. Any question about that? About this question? So the main idea of this problem is that if there is a work from U to V, you can always find a subset of the work such that it is a path, but it has no cycles on that. And I prove it by contradiction. If there's no question about this question, let's go to the next problem. I will give you 2 minutes to think about it, and then we will work on it together. So let's recall what is a bipartite graph. So if G is a bipartite graph, you can find a partition of the vertices have the partition that participate the vertices into two sets, and in each set, they have no edges, but they have edges between the sets. So this is a bipartite graph. And then you can use the definition of a bipartite graph to prove this problem. Okay, let's get started. Let's see. So because we needed to prove every cycle in G has even length, so we let C be a cycle in G with length of n. And we can write it as Z0 UO. Okay. We don't need to write down age in this proof, so it can be V0, V1, V2 to Vn minus 1 to V0. And because it's a cycle, so the starting point and the end point should be 0. And then because we have NH in this cycle, so we say the length of this cycle is N. And then by the definition of a pi-type graph, we can divide the vertices into two sets. So there is a partition of the vertices. V1 and V2. And suppose V0 is an element of V2, then V1 is an element of V1. So this is by the definition of a pi-type graph, because vertices that form this cycle must be alternative between V1 and V2. Otherwise, if we say V1, or if we say Vi and Vi plus 1 is in the same set, then there will be an edge in V1, which is not allowed in a pi-type graph. But we needed to write it down. So we know V0 in V2, V1 in V1, V2 is in V2, V3 is in 1. And then so we can conclude V2K is in V2 and V2K plus 1 is in V1. Any question about this statement? So this, in other words, that means the vertices with even index is in V2, and vertices with odd index is in V1. Sorry, this should be lower number. So, and also because V0 is in V2, so Vn minus 1 is in V1. Because Vn minus 1 is immediately before V0. So Vn minus 1 is in V1. This is because V0 is in V1, and so n of Vn minus 1 should not in V1, should be in V2. Oh, sorry. V0 is in V2, so Vn minus 1 should be in V1. And because Vn minus 1 is in V1, we know n minus 1 is odd number. Because we know the vertices with odd index, the vertices whose index is odd belongs to V1. So we know n minus 1 is an odd number, which means n minus 1 is equal to 2k plus 1 for some k is an integer. So n is equal to 2k plus 2. It is equal to 2m, where m is equal to k plus 1, and m is an integer. So therefore, n is even. Because n is the length of the cycle, so we say C has evenness. So we are done with this. So cycle C has evenness. Now we are done with this question. Any questions so far? Okay, then let's go over two problems from quiz 5. First one is quiz 2. Question 2. I think this is the hardest problem in this quiz. So in this problem, we need to form 7-digit string with 9 number. And in this problem, the order doesn't matter. So we can rewrite the problem in another way. That is, let ni be the number of times to choose I in 4-digit string. Then we can know n1 plus n2 plus n3 plus n9 is equal to 7. So this means if we have n1 equal to 3, n3 equal to 3, and n9 equal to 1, then we will have 3, 1, 3, 3, and 1, 9 in the digit string. So we want to, so the question is that the question can be converted to know how many possible combinations or solutions to this equation. So we can treat it as a bad problem, which is n plus r minus 1 choose r. Here, n is equal to 9, r is equal to 7. So it is equal to 15 choose 7. Any any question about this this part? Okay. Then let's go to the next one. In part B, we need to show the possible solutions, but has no more than 2/7. We can use two ways to solve this problem. The first way is that we can use the number of all possible answers without constraint to 7. Minus the number of the possible combination such that the string have at least 3/7. So we have already know the answer for the first item, that is from part A. We know it's 15 choose 7. So for the first item is 15 choose 7. So what we want to know is what's the value of the second item. So for this one, we can still use the notions from part 1, but we needed to have a small modification to that. This is the original one, but in part B, we know we want to calculate the number of combinations that the string has at least 3/7. So if we minus 3 on N7, then this item is still non-negative. And then we need to also minus 3 on the right-hand side. Now we can rewrite the back problem as Cn plus R minus I choose R. And N is still 9 because we have 9 items from the left-hand side. But now the R is equal to 4. So it is equal to 12 choose 4. So the final number for this problem is 15 choose 7 minus 12 choose 4. I would say this is the first way to solve this problem. Still, we have another way to solve it, is that we can calculate the number of combination such that the string has no 7 plus the combination such that the string has 1/7 plus the number of the combination such that the string has 2/7. So this is another way to do that. In this way, we need to have three different cases. So for the first one, okay. So for the first one, we say the combination such that the string has no 7s, which means we should have N1 plus N2 plus N3 plus N6 plus N 8 plus n9 is equal to 7, which means we don't have n7 in this equation. Now we still can use the back problem, but now n is equal to 8. So it is equal to 8 plus 7 minus 1 choose 7. It's equal to 14 choose 7. And this is the solution for the first case. And in the second case, we said we have 1 7 in the string, which means n7 is equal to 1. So okay, I will write it in the previous page. Oh, no place. Okay, we can start it from here. So we want to know the number of the combinations that has 1 7. The string has 1 7. So we have n1 plus n2 plus n3 plus n6 plus n7 plus n8 plus n9 equal to 7, and n7 is equal to 1. So if we can remove the n7 to the right-hand side, then we have n1 plus n2 plus n9 is equal to 6. Where in the left-hand side there's no n7, so if we treat it as a back problem, n is equal to 8 because we don't have n7 on the left. So it is equal to 8 plus 6 minus 1 choose 6. It is equal to 13 choose 6. And similarly, we needed to calculate the third case, the number of the combination where the string has 2 7s. So in here, n is equal to 2. So just similarly with the previous one, here we have n is equal to 2. And we can also move the 2 to the right-hand side. Then we have n1 plus n2 plus n6 plus n8 plus n9 is equal to 7 minus 2 is equal to 5. So the back problem becomes the n is equal to 8, r is equal to 5. So it's 8 plus 5 minus 1 choose 5. It is equal to 12 choose 5. So we needed to add the 3 cases, then n is equal to the first one is 14 choose 7 plus 13 choose 6 plus 12 choose 5. So this is the second way to solve this problem. Both this one and this one is correct. Any question about the question 2 from quiz 5? Okay, let's go to the next problem. Question 3 from quiz 5. So the first one, we needed to calculate the probability the children appear in line in alphabetical order by name. So PE is equal to NE over NS, where S is the sample space. So we have 30 children and the order matters. So it is 30 permute 30. And we only have one way to satisfy the NE. So it is equal to 1 over 30 factorial. And this is the answers for part A. Then let's go to part B. We have 15 fifth graders and 15 fourth graders. So if we want all fifth graders precede fourth grader, so for each graders, we have 15 factorial ways to form the line, and also this way. So PE is equal to NE over NS, while NS is still 30 permute 30, and NE is 15 permute 15 times 15 permute 15s. It is equal to 15 factorials times 15 factorials over 30 factorials. And this is the answers for part B. And finally, we needed to calculate the probability that they alternate by grade in line. So okay, I will. So if suppose this is the first children, and then we need the children in green to be the same grader, and also the children in blue are in the same grader. So still we have for the green ones, we have 15 factorial to permute them, and we also have 15 factorials to form the line for the blue graders. And also we can choose the first one to be fourth grader or to be the fifth grader. So we should times 2 for NE. So the probability of E is 2 times 15 factorial times 15 factorials over 13 factorials. And this is the answers for this question. Any questions so far? If you don't have other questions, then we are end for today's discussion session, and good luck for the quiz or for the final.
Thank you.